So then let me give you a definition. So on Monday, we had talked about the general antiderivative, right? Where you just, so for the last example that we did was that h of x equals e to the 4x. And we found that capital H of x was equal to 1/4 e to the 4x plus c, right? And so this is just the most general. And so we say that the collection of all of them, right? So like all of the ones with the different values for c. So the collection of all antiderivatives of little f is called the indefinite integral of little f with respect to x and is denoted by, and so it's going to be that integral symbol. So if you've seen it before, then you should recognize it, but it's given by, it's like this, it's a really like elongated s, right? And then, so this means the integral of f of x with respect to x so this part is the integral. This piece right here is called the integrand. And then this is the variable of integration. And so basically an integral, it's just an antiderivative, but it's all of the antiderivatives that you could have. And so here, what's it called? So example, so let's just evaluate each one of these. And we're gonna have the first one is gonna be the integral of 1 over x squared minus x squared, oops, minus 1/3 dx. So what I'm allowed to do, integrals have very similar rules as derivatives, right? So if I were to find the derivative of x squared plus x, I could find the derivative of x squared first, and then I could find the derivative of x, and then I could just add their derivatives together. And so integrals work almost the same exact way. And so I can do the integral of 1 over x squared first with respect to x. And then I can subtract it from the integral of x squared dx. And then I can subtract it from the integral of 1/3 dx. And so what did I have to integrate to get 1 over x squared? So you can if it helps to think about it, 1 over x squared is equal to x to the -2. And when I find antiderivatives, what do I add to my powers? Yeah, you're gonna add 1. And so at some point, I definitely had x to the -1. Those aren't equal. But I definitely had x to the -1. And so should this be positive or negative? If I have positive over here, then should my like antiderivative be positive or negative? So if I just take the derivative of this as is, I get -1 over x squared. So what do I need to make my antiderivative over here? Yeah, it needs to be negative. And then minus, so x squared, if I focus on that, so x squared, at some point, right, I'm gonna again add 1. And so at some point I definitely had x cubed. But when I take the derivative of x cubed, I get 3x squared. So what do I have to multiply my antiderivative by? Yeah, 1/3. And then whenever you have a constant, what do I just need to attach to my constant when I find its antiderivative? So what did so that's going to be at the very end, but I'm still missing something right here. Yeah, that x, right? And so the constant, that's what's going to go at the end. But so here, what I meant by differentiating a constant or integrating a constant is right here. I just have a constant next to the integral sign. And so when I take the integral of just a constant, I just add an x right after it, right? Because then when I take the derivative, the x just goes away. And so here, this is the answer. So is everybody okay with that one? Do you have any questions? Okay. So then let's look at part B, which is the integral of 2x times 1 minus x to the -3 with respect to x. So real quick, if I were to ask you to find the derivative of x squared sine of x, can you say that this is equal to the derivative of x squared times the derivative of sine? Is this true? Yeah, no, this isn't true, right? And so same way, like the same thing with derivatives, you can't just like, there's the product rule, right? It's a lot more complicated than just these two pieces. The integration works very similarly, right? So I cannot say, so I'm going to erase all of this. And so I'll add, this is not equal to the integral of 2x dx times the integral of 1 minus x to the -3 dx. And so you're not allowed to do that. And so here, what do you think I'm going to do instead? What can I do with this 2x? Anybody? So what can I do with this 2x? It's actually the exact opposite of take it out. Yeah, you can distribute it to both of these pieces here, right? And so when I do that, then all I have is subtraction, right? And so I can do exactly what I did in part A. And so I can focus on 2x dx, and then I can subtract it from 2x to the -2 dx. Does that make sense? And then here, okay. And then here, so what's the antiderivative of 2x? What do I need to do to the power on x? Yeah, so you're going to take your x and you're going to add 1 to that power, right? And so you're going to get you're definitely going to have x squared. And so do I need to do anything else with this x squared? When I differentiate this, do I get 2x? Yes, so that's perfectly fine. There's the antiderivative of that first part. Now I need to look at 2x to the power of -2, right? And so here, I'm still going to add 1 to my power. So I still have that -1 right there. But then what do I need to include out front? When I differentiate this, I don't get x to the -2 or 2x to the -2. Yeah, I'm gonna need a 1/2. Is it a 1/2? Wait a minute. X to the -1. And I do this, I'm gonna get, oops, not derivative, -1 over x squared. Yeah, so I would need that 1/2, right? But then what else am I gonna need? Because if I look at, yeah, so I'm going to need to make it negative, so I'm going to need to make that positive. And the reason for that is because if I differentiate the positive version of this, then I'm getting the negative, right? And so that's how I want to go from positive to negative right there. Yeah. Okay. So then what do I need to include after this part? Yeah, the plus c. And so that's the answer here. So are there any questions about these first two examples from today? Is this making sense going backwards? Okay. So then, oops, part C, let's look at the integral of 4 plus the square root of t all over t cubed dt. So again, I can't take this and split it across that division, right? Oops, I can't say it's the integral of 4 plus the square root of t all over the integral of t cubed, right? I'm not allowed to say that. And so again, I'm going to have to figure out something algebraically to do to this so that I can find the integral. And so what can I do with that t cubed? Yeah, I can make it t to the -3, and then I can distribute it, right? So 4, or here, let me do it this way first. So t to the -3 power times 4 plus the square root of t dt. And so then you can distribute it and you get 4 t to the -3 power dt plus the square root, the integral of here. This is, so off on the side, I'll do this. So t to the -3 times the square root of t. What power can I put on that square root or change that square root to? Yeah, 1/2. And then what am I going to do with these exponents? Am I going to add them or multiply them? Yeah, you're going to add, and so you're actually going to get t to the -5/2. Oh, I'm going to have to, uh-oh, that's not good. Okay, and then so here we get t to the -5/2 dt. And so then when I look at the antiderivative of t to the -3, I add 1 to the power, so I'm definitely going to have t to the -2. But then I need to figure out how that 4 got there, right? So when I differentiate t to the negative 2, so d dt t to the negative 2, you get negative 2 t to the negative 3. So what do I need to multiply this by to get to 4 t to the negative 3? Yeah, negative 2, which means I need to include the negative 2 out front here. And then again, I'm going to do the same exact thing. I'm going to add 1 to the power of negative 5 over 2. And so I know I definitely have negative 5 over 2 plus 1. I think my notes are wrong. So plus 2 over 2. That's negative 3 over 2, right? Yeah. But then when I differentiate t to the negative 3 over 2, I don't get t to the negative 5 halves. So what do I need to multiply it by? Oops. Because when I differentiate t to the negative 3 over 2, you get negative 3 halves t to the negative 5 over 2. So what do I need to multiply by? Because I essentially want to get rid of this negative 3. Yeah, so negative 2/3. So I wouldn't have plus right here. I'd have minus. And then plus c. And so there's our answer. So does anybody have any questions about these problems? For B, the antiderivative be 1 over 2x to the negative 2. No, you shouldn't have negative 2 in the antiderivative, because here, so what you're doing is you're adding 1 to that power, and so that's how I got negative 1. But then if I focus on just x to the negative 1, if I take the derivative of that, I get this with positive 2 down there, which is how I have negative 2 up here. Does that make sense? Oh, and the reason I have negative 2 here is because I distributed this. And so I have x to the negative 3. And so I really have this, right? And so I cancel this and I just have 1 over x squared. So to the, okay. Okay, yeah, so just make sure when you distribute correctly, or when you distribute that you're like working with the exponents correctly. But so are there any other questions? Okay. So then I need to hang on real quick. Okay, so in this section, we are going to, find areas under curves using very archaic methods, but that's okay. It's gonna set up for us the actual, like another, like what the integral represents in like real world terms and stuff like that. And so we're not actually gonna be integrating using the antiderivative until we get to section 5.3. And so I'm just gonna kind of introduce this material. It's not stuff that's really like useful to do. And so you're not gonna have too many homework problems about it. It's mostly just gonna be, do you understand what's happening here? And then in 5.2, like it's basically it's the building blocks that we need for 5.2 and 5.3. But so let's get started. So here, the first thing we need to talk about is I'm gonna give you like that definition that I kind of just said. So integration is a method for finding areas and volumes. And so if you're going to go and take Calc 3 at Cal Poly, that's where you would learn about the volumes of this stuff. We're going to get into volumes a little bit, but like you're going to get into it more deeply in Calc 3. Oh, of general shapes. Sorry, forgot to include that. Right, because you know, or you should know how to find the area of like a square and of a circle, of like any sort of shape, right? Triangles, stuff like that. But if you're just trying to find areas of things that don't, or that aren't like generic, then you have to use integration. And so just like a little note, the definite integral. And so what I just showed you up above in 4.8 was the indefinite integral. That's not straight at all. But okay, so let's wait for Phil actually. Okay, there he is. All right, so here, let's draw a picture real quick. So it's gonna be a graph, and it's gonna be, so let's say I give you this picture, like some sort of graph that looks like this. And I tell you, oops, this is x equals 1, this is x equals y, and I ask you to find the area under this curve, right? Oh, it's not supposed to look like a circle. Make it look less like a circle. It's supposed to kind of look like, yeah, not a circle, or not a quarter of a circle. But so here, there is no formula for finding the area of this. And so what we're gonna do is we are first going to use rectangles to approximate the area. And so the number of rectangles that we use is going to be important, right? It's going to give us a better approximation. And so here, I'm going to start out by just making 2 triangles. If I go to like, let's say this is 1/2, comma 3/4. Then I can make a triangle, a rectangle. And then I can make another rectangle. Oops. Okay, that does not look like 1/2. Hang on, let me do this better. Oh, wow. So if this is 1, 1, then 1/2 is like there. And so I put the dot here, 1/2, 3/4. Here's one rectangle. Here's another rectangle. There we go. Okay, now that we've drawn the picture. What we're gonna do, so the heights of the rectangles are the max heights of the curve on that interval. Right, so here, the height of this rectangle is the tallest point of the curve from 0 to 1/2, right? Same thing right here. This is the like tallest point on the curve from 1/2 to 1, and it's also the height of that rectangle. And this is called, so definition, when, when the max height of the rectangle is the max height of the curve on that interval. The approximation is an upper sum. So to approximate the area, what do you think we're going to do? Like, why do you think I made rectangles there? What can I do with those rectangles? Yeah, you can find the areas of the rectangles and then add them, and you can say, okay, it's approximately equal to that. The only problem with that is that you have all of this space up here that we're also finding the area of that we don't actually want to include, right? But that is how we start. And so to approximate the area, find the areas of the rectangles and add, and this is getting, I'm not writing in a straight line at all. Oh, I guess now I am. Earlier I wasn't. Okay, but so here, you're gonna have the A, so for this picture, so I'll call this like picture A. So, oops. Oh yeah, if my iPad dies, which I don't think it's going to, but if it dies, then we're just gonna end class early. But so here, the area is gonna equal, or is gonna approximately equal, so you should put the squiggly equal signs. And so here, what I'm getting is the area of the rectangle is just equal to the